Hello viewers, welcome once more to Dr. J's Physics Lecture Series. For more notifications, prompts and follow-up, please remember to subscribe to my channel, like my page, drop your comments in the comment section. So now we want to check how we can use dimensional analysis to obtain a relationship between different physical quantities. From my previous lectures, we talked about dimensions, introduced it. Then we looked at how we can get the dimension of different physical quantities. We also checked how we can use dimension to see or ascertain if an equation is correct or not. This particular lecture series will look at how we can use dimensional analysis to obtain a relationship between different physical quantities. So on your screen, we're having that of a simple pendulum. We want to use dimensional analysis to obtain the relationship between the period of a simple pendulum, the length of the thread, and the acceleration due to gravity. So this is how we proceed. The question is there. So we are going to look at the equation that was given. In this case, we have that T is proportional to the power of the length of the thread, power of the mass of the bulb, and the power of acceleration due to gravity, G. So the first step to take in this problem is to express each quantity in terms of dimension. If you check the equation, all the quantities have been expressed in terms of their dimensions except acceleration due to gravity, G. So we have to express that in terms of dimensional analysis and proceed. So we say that T is equal to K. You can ignore the K since it's a constant, but in the end, it can be introduced into the equation. So K raised to power KL raised to power X, M raised to power Y. Then the dimension for acceleration due to gravity is L T raised to power minus 2. So all raised to power Z. So we can rewrite, let's exclude the constant K in our next equation. Later on, we introduce it. L raised to power X, M raised to power Y. We are going to expand these brackets. So we have L raised to power Z, T raised to power minus 2Z. Let's call this equation 1. We can apply one of the laws of indices. Since we have L raised to power X, L raised to power Z, then we apply that law that says when we have a single base, you have the same base, just choose one and add their power. So for this, we say L raised to power X plus Z, M raised to power Y, and T raised to power minus 2Z. Call this equation 2. Now we have L, M, and T on the right-hand side of equation 2. We have to introduce an imaginary L and M on the right-hand side because we have only T. So we introduce an imaginary L and M in a way that will not distort the equation in equation 2. So the only way we can do that is to raise M and L to the power of 0 on the left-hand side of equation 2. So we say M raised to power 0, L raised to power 0, and T raised to power 1 equal to L raised to power X plus Z, M raised to power Y, and T raised to power minus Z. Let's call this equation 3. Now, the next step is to equate the powers of M, L, and T. Say equate. Equate the powers of M, L, and T on both sides. Let's just leave this out. On both sides of equation 3. So for M, on the left-hand side, we have 0. On the right-hand side, we have 1. Call this one equation 4. For L, on the left-hand side, we have 0. On the right-hand side, we have X plus Z. Call this one equation 5. For T, on the left-hand side, we have 1. And on the right-hand side, we have minus 2Z. Call this one equation 6. Then, from equation 4, we've already seen the answer to Y. Equation 5, we have 2 unknowns, so we can't proceed with equation 5. But from equation 6, we can get the value of Z as follows. So if Z is 1/2 minus 1/2, we substitute that into equation 5 to get the value for X. So from equation 5, we say 0 is equal to X plus minus Z minus half, which is written as X minus half. So if we move this across the equality sign, then X will equal to positive half. So our answers are X equal to positive half, Y is equal to 0, and Z is equal to minus half. Now, the next step to take, we are going to substitute these values into equation 1. Oh, sorry, let's use equation 2. So we are going to substitute these values into equation 2 as follows. So I'm going to wipe out the question, then continue solving. So let's continue. So from equation 2, we say that T is equal to L raised to power X plus Z, M raised to power Y, and T raised to power minus 2Z. But remember the original equation. We'll substitute into the original equation, which says that T is equal to K, L raised to power X, M raised to power Y, and T raised to power, and G raised to power Z. So we'll substitute the values of X, Y, and Z into this equation. If we do that, T will be equal to K, Lx is half, Y is 0, and Z is minus half. M raised to power 0 is 1, so this can give us K, L raised to power half, all over G raised to power half. This is the same thing as saying K, L over G, all raised to power half. Any quantity raised to the power of half is the square root of that quantity. So this will be equal to K square root of L over G. But initially, we are told that K is equal to 2 pi. Therefore, our period T is equal to 2 pi square root of L over G. This equation is the equation for the period of a simple pendulum. So we have used dimensional analysis to obtain an expression for the period of a simple pendulum. Let's try another problem. So let's look at another problem. Here we have that suppose a fluid whose coefficient of viscosity is given there. We can see the symbol for density also. A fluid who has coefficient of viscosity, density, flows through a cylindrical tube of radius r and length L. If you check this particular problem, you discover that there is no equation given. So one has to extract the equation from the problem. So let's go on. It says that let P be the pressure difference in the liquid at both ends of the tube. If the volume of the liquid flowing per unit time through the cylindrical tube depends on the pressure gradient. So we are told now that the volume of the liquid flowing per unit time. Volume flowing per unit time is V over T. So we write that first. So we say V over T depends on the pressure gradient, meaning that it is proportional. The pressure gradient is P over L. That is pressure over length. The coefficient of viscosity, which is this, and the radius r. So this is proportional to the pressure gradient, coefficient of viscosity, and the radius. Of course, we are going to raise all these quantities to some powers. So let's say pressure gradient raised to power x, coefficient of viscosity raised to power y, and the radius raised to power z. Let's call this one equation 1. Of course, it can be written as this, introducing the constant k. So we say P over L raised to power x, coefficient of viscosity raised to power y, and the radius raised to power z. Let's call this one 1a, this is 1b. However, we can work without k. Later we introduce it at the end of the problem. The goal is to find the values of x, y, and z. Then resubstitute into our expression. How do we do that? We have to express every term in terms of their dimensions. So for volume, the dimension of volume is L cubed. So we say L raised to power 3. Time is T equal to the dimension for pressure. Pressure is force over area, which is M L raised to power minus 1 T raised to power negative 2. That is for pressure. All over length L, all raised to power x. Then the dimension for coefficient of viscosity, we've done that in our previous lecture series, is M L raised to power minus 1 T raised to power minus 1. We all raise everything to power 1. Then radius is the measurement of length, so L raised to power z. We can call this equation 2. This can further be expressed as L raised to power 3 T raised to power minus 1 is equal to m l raised to power minus 2 t raised to power minus 2 all raised to power x. Then of course m l minus 1 t minus 1 all raised to power y a raised to power z. Call this one equation 3. So we will now expand equation 3. We have all these quantities raised to some power. So we are going to expand these brackets. So on the left hand side we have L raised to power 3 t raised to power minus 1 is equal to, we are going to expand this first. So we have m raised to power x, then L raised to power minus 2x, t raised to power minus 2x. Then we expand this next bracket. We have m raised to power y, L raised to power minus y, and t raised to power minus 1. Then finally L raised to power z. Let's call this one equation 4. So we have L raised to power 3 t raised to power minus 1 equal to, we have m appearing twice, so we take 1 and add their powers. So m raised to power x, this is y, so plus y. Then take L. L is occurring 3 times. Choose L and add the power, so you have minus 2x minus y plus z. That's for L. Then for t, we have t appearing twice. So we say t raised to power minus 2x minus y. Call this one equation 5. So we have to equate. Before we do that, we have m on the right hand side of equation 5, m, l, and t. We only have l and t on the left hand side. We have to introduce an imaginary m. To do that, we just raise m to the power of 0. L raised to power 3 t to power minus 1 equal to m raised to power x plus y, L raised to power minus 2x minus y plus z, t raised to power minus 2x minus 1. Call this one equation 6. So all we need to do now is to equate the powers of m, l, and t. We equate powers of m, l, and t. On both sides of equation 6. So for m, on the left hand side we have 0. On the right hand side we have x plus y. Let's call this one equation 7. For L, on the left hand side we have 3. On the right hand side we have minus 2x minus y plus z. So minus 2x minus y plus z. Call this one equation 8. And for t, on the left hand side we have minus 1. On the right hand side we have minus 2x minus y. Call this one equation 9. If you check all 3 equations, we have 2 unknowns in equation 7, 3 unknowns in equation 8, and 2 unknowns in equation 9. We can't proceed, so we have to eliminate 1. it's easier to work with equation 7. So from equation 7, we can say that y is equal to minus x. So if y is equal to minus x, we can now substitute that into, let's say, equation 9. So from equation 9, we can say that minus 1 is equal to minus 2x minus, then anywhere you see y, substitute with minus x. So this expands to minus 1 is equal to minus 2x plus x. So let's proceed. So from here, from this equation, then we have that minus 1 is equal to, what is minus 2x plus x is minus x. So that implies that x is equal to 1. So substitute the value of x into equation 7. So using x in equation 7, gives, so we have in equation 7, 0 is equal to 1 plus y. So that y will be equal to minus 1. Since we have gotten the values of x and y, we can now substitute them into equation 8. So using x and y, in equation 8 yields, so in equation 8 we have 3 is equal to minus 2 into 1 minus y is minus 1 plus z. So that 3 will be equal to minus 2 plus 1 plus z. Minus 2 plus 1 is minus 1. So 3 is equal to minus 1 plus z. That implies that z is equal to 3 plus 1, which is 4. So z is 4. So I'm going to wipe the other part. Then we substitute the values of x, y, and z into our original equation to get an expression for the volume of liquid flowing per unit time. So x is equal to 1, y is equal to minus 1, and z is equal to 4. So we recall our original equation where we said v over t is equal to k into bracket of p over l, all raised to power x, coefficient of viscosity raised to power y, and radius raised to power z. So we substitute the values of x, y, and z into this expression. So we proceed by saying v over t. Remember, the question says k equal pi over 8. So we say pi over 8 brackets p over l all raised to power 1, coefficient of viscosity raised to -1, and arrow raised to power 4. This can be further expressed as v over t is equal to pi over 8, then p all over l times coefficient of viscosity arrow raised to power 4. So we can conveniently write this equation as V over T is equal to pi P r raised to power 4 all over 8L times coefficient of viscosity. So this is the expression for the volume flowing per unit time in the cylindrical tube. See how simple it is. So you have seen from these two examples that we can use dimensional analysis to obtain a relationship between different physical quantities. Now, subsequent lectures will also look at one or two problems on how to establish a relationship between different physical quantities using dimension. So don't forget to like my video, drop your comments in the comment section, and of course, remember to click the subscribe button so that when I upload subsequent videos, you get notifications when new videos are uploaded. Thank you.